FET, Field Effect Transistor. This is also a transistor but affected by field. That's why we call it as Field Effect Transistor. The topics that we are going to study in this is JFET, junction FET, E MOSFET, enhancement MOSFET, D MOSFET, depletion MOSFET, biasing of FETs, applications of FETs. When I say FETs, I mean all the three, both in applications and biasing. Let's see the first topic today. JFET, junction field effect transistor. First we'll see comparison between BJT and FET. BJT, it can work with both majority and minority carriers, bipolar. Whereas FET is unipolar, it works only with majority. In BJT, IC increases TJ increases IC naught, and that increases IC once again. So in this process, junction temperature is continuously increasing. That's why it is called thermal runaway. Here, no thermal runaway. In fact, here also there is a temperature, but not cumulative. For example, drain current will create some temperature, but there is no minority current. That's why there is no cumulative problem. That's why there is no thermal runaway. Third one, thermal unstable. FET is also thermally unstable because instability is all there in every device, but thermal runaway is available only in BJT. IC function of IB and VC, that means input current is controlling, that's why it is called current control device. Whereas in FET, ID is function of VGS and VDS, that's why input is voltage, so voltage control device. In BJT, power dissipation is high because input current is there. In FET, power dissipation is low. Fifth point, input current is not zero because IB is not zero. That's why RI is low because input is forward. Input current is zero because input is reverse biased. RI is infinity. In BJT, R0 is high because output is reverse biased. Whereas in FET, output is a channel, that's why resistance is low. Output current is large, more driving capacity in BJT. In FET, output current is small. Eighth point, AV is greater than 100, AV is less than 10. In BJT, voltage gain is more than 100. In FET, AV is less than 10. Ninth point, BJT is a bulky, FET is a small device. 10th, because of temperatures, BJT is noisy, but FET is immune to noise. So these are the comparisons we have. So in general, FET is very much preferred, but there are only two drawbacks. Output current is less, gain is less. Except these two, in all aspects, FET is good. Then classification. Classification of FETs. FET is JFET, the symbol is this. MOSFET, E MOSFET, enhancement MOSFET, depletion MOSFET. Then this is the symbol. No permanent channel, that's why dotted line. Permanent channel, thick line. But where D means drain, gate means G means gate, S means source. But what is the arrow here? Arrow shows conventional current when the junction is forward biased. For example, if the junction is forward, this arrow is here. First take a junction, take this terminal, forward bias. In N channel, this is P. P means forward bias, current is this. Similarly, this is N channel, N is given to negative, therefore current is flowing in this direction. Permanent channel here. In this N channel, N is given to negative forward, current goes this way. So these are all the symbols for N-type, N-channel JFET as well as MOSFET. Only for the convention, only for telling the arrow, I have forward biased. Otherwise, FETs are never forward biased. In fact, JFET, it is reverse bias at input. That's why only for the arrow I have developed this concept. Not only for FETs, this statement is valid for every device. Arrow shows conventional current when the junction is forward biased. Now let's go for manufacturing. How do people manufacture this? For example, N channel is there. You are given some voltage. How is this biased? You cannot say bias because there is no junction. You can say biasing is given, but you can't say forward or reverse. That's why we only say junction is biased. I mean, this channel is biased. Okay. When you vary VDS, current will increase. For every change in VDS, there is an increase in ID. When there is a change in ID, we call this as ohmic region because it is behaving like a resistor, so people call it as ohmic region. In this, no constant current characteristics. In fact, we always require constant current characteristics for any device to act as an amplifier. That's what we saw in BJT. But now it is not there. That's why it cannot act as an amplifier. And then what is acting for? It is acting like a resistor. So that's why this is called ohmic region. Okay. Then how to achieve constant current characteristics? To achieve constant current characteristics, we must introduce heavily doped gate. For example, this is channel and this heavily doped you have to introduce. So when you introduce this heavily doped, you know what happens there? Heavy doping here. Then even without any bias, whenever there is a P and N, there will be junction. There will be junction. Bias at the gate is only to increase the or change the width but not to form the width. Because even under open circuit conditions, there is a junction, there is a formation of junction. So P plus N is an equation is here. And this is channel width here. Then let us see what is happening. First, biasing. What type of biasing I should give at the input? Suppose if I give forward bias, junction width will decrease, channel width will increase, current will increase. You will still get ohmic region. But if you reverse bias it, junction width increase, that means channel width decrease. Suppose if you reverse bias this, junction width will increase, channel width will decrease. That's why we have to give reverse bias at the input. That by decreasing channel width, the current is controlled, collisions will come, constant current will come. When the constant current is coming, we call it as amplifier. That's our desire. Then how to dope at the gate? So when you want to really dope at the gate, you have to go back to diode. For example, this is P++, heavily doped. This is N. 2 ions here and 2 ions here. And the number of ions always equal, but the point is widths are different. When the widths are different, what should happen is there's a more increase in the lightly doped side. So if it is simply PN, it's a linear graded junction, equal increase both sides. But if it is P plus N, it is unequal, therefore increase of junction width is also unequal. When the increase of junction width is unequal, what is happening? Automatically the width increases more into lightly doped. Therefore, gate is heavily doped and reverse bias to increase junction width more into the channel. Thereby, we achieve constant current characteristics. Remember two things. Input should be reverse biased for the junction to increase, junction width to increase. And that gate must be heavily doped so that more increase of the junction width into channel. Then only you can have what you call more junction width, channel width decreases. Then let's talk about pinch off voltage. With reverse bias at input, If VGS increase, junction width increase, channel width decrease, current is controlled. But if VGS further increase, junction width further increase, channel width further decrease, current still decrease. Lastly, if VGS is minus VP, then the channel width becomes 0 because junction width will completely increase, both the junctions will come and touch each other, junction width is 0, therefore ID is 0. That's called a pinch off voltage. From now onwards, pinch off voltage means where current is 0. Now let me get back to the diode. Vj is equal to Q and D by 2 epsilon Wj square. Now in the place of J you have 2A. 2J is equal to 2A. Therefore width is A. In the place of here I put A. Now we look at this. Q is a charge constant, doping is constant, 2 is constant, epsilon is constant, A is also constant. Therefore the total pinch off voltage is fixed for a given device. As you change device to device, there may be change, but otherwise it's fixed value. Okay. So from now onwards, everywhere remember, VGS in terms of VP is fixed. That's where ID becomes 0. Then drain size. Generally people think a drain and source can be interchanged. I am talking on that. Drain is slightly larger than source as drain has to withstand temperature. Because when carriers are going from source to drain, they will be accumulated there and their need is some little larger. May not be as large as collector, but little larger. Therefore, in principle, drain and source can be interchanged, but in practice it is not preferred. It's not interchanged because drain is slightly larger. Then what is substrate or shield? See, when you look at BJT, input is forward, output is reverse. When you look at FET, input is reverse, that is true. Output you can't say forward or reverse. You know why? Because there is no junction. When there is no junction, you cannot say that. You can only say biased, but we can't say forward or reverse. Then characteristic equation, ID is function of VGS, VDS, external field. Because this is a field effect transistor, external fields also may affect on that. So if the shield is grounded, then external fields are also grounded. Suppose if some fields are coming, they will be. If some fields are trying to affect the device, they will be grounded if you ground the shield. That's why the fourth terminal in the gate is called shield, because it will shield the device from external field. It is to protect the device from external field. That's why that has to be grounded if the fields are considerably large. But in the laboratories in the college, the fields are very less. When the fields are less, we can neglect it. That's why we never, I think most of the students would never see that the shield terminal is grounded. In fact, that has to be done if you really want the perfect things. But instead, I saw some people that they put this shield into the sky as if they are saying the field is invited. So ultimately, the shield has to shield the device from external fields by grounding it. Therefore, that fourth terminal called shield or substrate is grounded. Then of course, if the fields are grounded, then automatically if shield is grounded, fields are grounded, the external fields are neglected or removed. Therefore, the function is only in terms of input voltage and output voltage. And the input is affecting, that's why we call voltage control device. FET is voltage control device. Now, I am going to characteristics. I am dividing basically the lecture into 3 parts. First one is manufacturing, second is characteristics, third is equation. Now let's go to second part, that is called characteristics of a FET. Look at here. Please look at this carefully. You have given a negative voltage, reverse bias. And I am saying VGG is equal to VGS because there is no resistor and there is no drop. Similarly, VDD is equal to VDS. There is no drop. And then for different values of VGS, I have to plot ID and VDS. That is called output characteristics. And for different values of VDS, I need to draw for ID and VGS input. That's called transfer characteristics. Good. Now, let us go to characteristics. Say for example, VDS versus ID. That means VGS is a fixed value. Fix VGS at 0. For every increase in VDS it increases. After some time called pinch off, it becomes almost constant. That constant value is called constant current characteristics or linear region or amplifier pinch off. Pinch off means eaten off. Something as if something is eaten off, though the voltage is changing, current is not changing. Therefore, we call it as pinch off. Then look at this, VGS is minus 1. When VGS is minus 1, what is happening is, VGS is minus 1. There is again the same characteristics but slightly decreased, because when VGS increase, junction width increase, channel width decrease. Similarly, look at this red curve. For VGS is minus VP, current is 0, but that's why VGS VP. Then what is the relation between this VP and this VP? This is VGS, this is in terms of VGS, whereas this VP in terms of VDS. But therefore, pinch off in terms of VDS means from where ID becomes constant. In terms of VDS, from where ID becomes constant is called pinch off. In terms of VGS, where ID becomes 0 is called pinch off. Therefore, we have two meanings of the pinch off. In terms of output voltage, wherever ID becomes constant, it is called pinch off. In terms of input voltage, wherever ID is 0, it is also called pinch off. Both are pinch off. But the beauty is, this pinch off and this pinch off are numerically equal. The VP in terms of VGS, VP in terms of VD, they are numerically equal. That's why they are called both pinch off. Then how to calculate drain resistance? Drain resistance is calculated as change in VDS by change in ID. Say for example VGS is 0, and that is called pinch off region. This is pinch off for VGS 0, this is pinch off for VGS minus 1. So take only in the pinch off, because in that pinch off it is acting as amplifier. Then you can say it is the resistance of an amplifier. Otherwise, you cannot say. That's why you must take only in the pinch off region. Now look at, because even for VGS 0, this is pinch off. This is ohmic region. This is breakdown region. There are three regions for VGS 0. But there also you should take only pinch off region. And in the pinch off, it is very difficult to get characteristics, because take 2 points here ID, take 2 points here VDS. Change in ID is very small, that's why it is 10 kilo roughly. So don't take in ohmic region, because so many students asked me saying that, sir, this is very good to take, why not we take 2 points here, 2 points here, get the drain resistance. I said no, because that is not an amplifier region. You want drain resistance of amplifier. So take only in pinch off region. Next, for VGS 0, 0 to VP, there is a ohmic region. As VDS increase, current increase. For VDS, VP to VDS sat, as ID increases, collisions also increase, therefore ID decrease. If VDS is greater than VDS sat, then breakdown occurs. That's why never operate in breakdown region. That's about VGS 0. Now if I say VGS minus 1, what happens? Same thing repeats, but current decrease, because junction width increase, and then channel width decrease, current decrease. So VGS minus 1, that happens. For VGS minus VP, what will happen? VJ is very much increases, then WC decrease, okay, ID is automatically 0. So never operate FET in the breakdown region. This is all about output characteristics. VGS 0, VGS minus 1, VGS minus P. Between 0 to VP, VP to VDS sat, above VDS sat. This is all about, and from there if you calculate drain resistance, you get 10 kilo. So 10 kilo ohms is the resistance we get. Okay. Then let us talk about transfer characteristics. What do you mean by transfer? ID versus VGS. Actually, if you want input characteristics like FET, it is not possible, because input current is 0. When input current is 0, you cannot have input characteristics. So that's why I am drawing for only transfer. So take ID, VGS, where both become 0. There are two options for pinch off value and one ohmic region. That means take VDS pinch off, draw for VGS ID. Take VDS ohmic, draw for VDS and ID. You will get two different characteristics, but both should overlap at the same point because Vp is fixed for a given device. In spite of it, if you take all values of VDS in the pinch off, they'll get only one curve. That means they'll overlap. So this is better. This is better than this. Even if you take by mistake, one in pinch off, another in ohmic, the best suggestion I give is take 2 points here. 2 points in Vp, 2 points in ID. That is called pinch off. So take 2 points here and then draw this. And don't take GM, but that must be taken always in pinch off, not in the ohmic region. So what I mean is, if you see the characteristics here, whatever the pinch off you have seen here, Vp to VDS side, for example, this is 4, this is 20. Any value of VDS you take between 4 to 20, you will get what? You will get only one type of characteristics. This is characteristics. That's why 2 milliamperes per volt. And ID is function of VGS and VD. So what I am drawing is, I am drawing for ID versus VGS with VDS as constant. So as the VGS increasing, at one point, as VGS increasing, junction width increase, channel width becomes 0. When the channel width is becoming 0, you call it as pinch off, 0 current. Then amplification factor. Amplification factor is change in VDS by change in VGS. That means output voltage by input voltage, output by current, current by this. This is called RD, this is called GM. The total is mu is equal to GM into RD. Suppose GM is 2 milliamperes, RD is 10 kilo, the total is 20. So therefore, mu is equal to 20. Very unfortunate, the maximum voltage gain possible is 20. That's why practical gain is less than 10. You must have got in your experimenting in the colleges where you studied, that is around 7 to 8 gain you must have achieved. That's not possible. Then, now let me take you to, after characteristics, we generally go for equation. We are equation of a JFET. When you see this ID and Vp, what is happening? ID versus Vp is like a parabola in terms of VGS and Vp. Therefore, ID is IDSS into 1 minus VGS by Vp whole square. It's like a parabolic equation. But the good thing you can see from the characteristics and the equation here. Put VGS 0, ID is IDSS. Come here. This value is called IDSS. Put ID 0 in the equation, VGS is Vp. Therefore, that is one thing. Therefore, you have seen the maximum value is here, maximum value is here. Then how to understand the values? Because square is there, no. When you have a square, you should understand if there are two values, how to choose. That is, ID is generally less than IDSS because ID can never go beyond IDSS, VGS can never go beyond Vp. Modulus is used because they may change. The point is, polarities may be there. That's why modulus is the best one. So VGS is generally below Vp because above Vp, current is 0. So this is brief idea about an equation. We didn't derive it, but we are taking it and going to continue from there. Choice of VGS, ID and VDS. See, VGS and Vp, they belong to same polarity. ID, IDSS and Vp, VDS, they belong to same polarity. Therefore, for N channel, negative, positive. You have seen that characteristics also. VGS is negative, ID is positive. For P channel, positive and negative. What's the condition? VGS should be less than Vp, ID should be less than IDSS. This is the condition we have. Illustrative problems. They generally illustrate the concept because too much of theory is not good. That's why examinations, examples are good. First one, why, question number 1, why input is reverse biased? Look at here. Input is reverse biased to increase the junction width, thereby to decrease the channel width so that current is controlled and constant current characteristics is achieved. So this is increased, constant current is achieved. Look at 2A here, that's original channel width, 2B of X existing channel width, 2VJ of X junction width, because X is from here and whatever that I take it here, I call it as 2W of x here. So please remember, 2A is fixed but 2B is variable because junction width is variable. That depends on x where you take. What is 2B here? 2W, total 2A minus 2W of x. Therefore, A is B minus W. That's the meaning here. That's the purpose. The very purpose is to give the reverse bias at input so that it can increase the junction width, channel width is decreased, and that happens there. Why gate is heavily doped? Look at here. If gate is heavily doped, the purpose is to increase the junction width more into the channel which is lightly doped, and thereby there will be a collisions and constant current characteristics is achieved. Therefore, the junction is a step graded junction, and you know for a step graded junction Q and D by 2 epsilon WA square. That's the meaning. That's the purpose why we have gone for increasing junction width. Third question, problem. Define pinch off voltage. When you say pinch off voltage, the voltage that you give at the gate should increase and the junction width should increase. At one point it becomes 0. So it is a value of VGS for which ID is 0. That means 2B of x is 0. 0, A minus W. So therefore A is equal to junction width. Therefore VP is equal to Q and D by 2 epsilon junction width. In the place of junction width I can put A. A is a fixed quantity. Therefore, pinch off voltage is fixed for a given device. So fixed value is there. Question number 4. Why junction width is large at a drain than source? Normally people say both are equal, but there is a slight difference. The junction width is distributed along the length of the channel, and source, the carriers are starting from the source and then ending at the drain. Therefore, it is small at the source and large at the drain. So as you go distributed, voltage is getting added and added and added. Therefore, junction is more at the drain, less at the source. Question number 5. Define pinch off voltage in terms of VDS. In terms of VDS, look at here. In terms of VDS, where it becomes constant, ID becomes constant. In terms of VGS, where ID becomes 0. And these are the definitions of. So there are two definitions. One definition of where ID becomes constant, that is in terms of VDS, is called pinch off. Where ID becomes 0, that is called also pinch off. This and this are numerically equal. This is for VGS 0. VGS is 0 called VPO, and VP here are numerically equal. That's why we call both as pinch off. But remember, sometimes we call this as VGS cutoff. VGS cutoff means basically current is 0. So when current is 0, it's called VGS cutoff. Then sixth one, how to get GM? GM is generally dou ID by dou VGS. Take your equation here. ID is IDS into 1 minus VGS by VP. If you really do a differentiation, you will get these things. Then ID by GM, you will get half of VP minus VGS. And if you substitute in the place of 1 minus VGS, ID by VDS, you will end up as GM 2 by VP root of ID into VGS. These are the different expressions for GM. Seventh question. How to get RD? RD means drain resistance. Drain resistance is VDS by ID. In fact, this is AC, this is DC. AC is always less than or equal to DC. That's how we get drain resistance. But if you calculate it, derive it analytically, L by 2A Q N D Wn mu n into W 1 minus VGS by VP whole power half. Now look at here. If VGS 0, this becomes RD maximum. If VGS is 0, this is the maximum value. 1 by maximum is minimum. If VGS is VP, this is 0, therefore infinity. Therefore, RD changes from minimum to maximum, and that minimum is generally 3.5 to infinity for BFW 10 or 11 device, and therefore you can normally take 0 to 10K, because for VGS 0 it is roughly at 10K. So that's the drain resistance. What is zero drift drain current? Obtain a condition and the reasons for zero drift drain current. Now let me see that. ID versus VDS, two different characteristics, but both of them are beating at one current. That's called zero drift because the drift in this current is 0. As temperature increases, collisions increase. Then ID decreases by 0.7%. Because when the temperature increases, they move very fast. When they move very fast, they collide. When they collide, the amount of current will decrease. And that's 0.7. So 0.7% means 0.007 ID. Whereas the second way is, as the temperature increases, junction width decrease. And when the junction width decrease, channel width increase. When the channel width increase, current will increase. So first effect, current is decreasing. Second effect, current is increasing. If you can equate that increase and decrease, you will get a neutral condition. That condition is called zero drift drain current. So dou ID by dou VGS is the value that you get. GM by ID by GM is half of VP minus this. You already know it. Therefore, VP minus VGS is 0.628 is called condition for zero drift drain current. If you maintain this, the ID is going to be the most stable. Calculate mu. Mu is GM RD. So suppose GM is 2 milliamperes per volt, RD is 10 kilo, so roughly this value is 20. That's the calculation of GM. GM is 20. What is the significance of GM? Let me say that. If you see GM in any voltage, any amplifier, gain is GM-RL. If GM changes, gain changes. So gain is restricted with the value of GM. Gain is restricted with the value of GM. What is the significance of input? When you look at the input, if input is reverse bias, current is 0, power dissipation low, and the input voltage is controlling, and therefore input impedance is high, output impedance is low, voltage gain is less than 10. These are the things that are happen as far as JFET is concerned. When the input current is 0, input resistance is infinity, we call it as power dissipation is less. 12. What is the significance of RD? What exactly we find there? Look at here, RD. RD is VDS by this L by 2Q. ND mu n into W, 1 into VGS by VP. As VGS increase, this current, this RD is increasing. Therefore, when RD is changing with voltage, it's called voltage variable resistor. Voltage variable resistor. VVR we call it. What are the applications of JFET? Applications of JFET are: first one, as we just now studied, voltage variable resistance. As VGS changes, resistance will change. It acts as an amplifier because it also possesses constant current characteristics. It will act as a switch because above VGS VP ID is 0. It is acting as a reactance because there is a junction, there is a capacitor, there is a reactance. In fact, FET FM direct modulator or FM direct reactance modulator is from FETs. No cut-in voltage, because just like diode 0.6 cut-in voltage, in BJT 0.6 cut-in voltage, but here there is no cut-in voltage. That's why it's a good for signal chopping. Chopping means where you want to cut, you can cut it. If it is BJT, you can cut only 0.6 above. If it is a diode, you can only cut 0.6 above. So this is called no cut in the voltage, therefore good for signal chopping.